So the applications part, we can have any function that relates any two quantities. So whenever we have to figure out some kind of average, it will be over two particular points. And then, this can be related to the slope of a secant line, and you can find the difference of the y's, of the difference of the x's. So, for example, in this application about density, they were talking about density as the division of mass by the length. So if, for example, you have units as kilograms for mass and for length you have meters, then you can measure some kind of average density. So that would just be the change in mass divided by the change in length. And the units will be whatever you have for mass, kilograms over meters, and that will be fine. And this is something that in previous courses we could have found easily, and we don't need calculus for that. But the interesting thing is that we can find the linear density at some particular position on a wire, so we don't need the measurement for 2 points, we just need the measurement for 1 point. So I don't want to know the average density between meter number 3 and meter number 5 in a wire. I can just look at what happens at the third meter on a wire. So what is the linear density at that point? I don't have an average density. I can have the instantaneous rate of change of mass over length, or the derivative of this, which would be the limit as the change in length approaches 0 of the change in mass divided by the change in length. So if I have an equation that relates mass and length, I don't know, f of x equals whatever, e to the x or any other function, the linear density at one particular spot on the wire wouldn't be anything but the derivative of that function evaluated at that number. Isn't that beautiful? We can find the linear density at one point without the need of taking the average by having 2 points. So the same case happens with other situations. For example, it was talking about charge, how the charge, when particles are charged, positively or negatively. I don't understand the physics of that. That's why I didn't go into physics. But we can have a function that relates charge in coulombs. You can ask Mr. Maggiore to read that for you, because I can't apparently. Over time, the average current, you can find it between, I don't know, 10 and 20 seconds, and it will be again the difference in the charge divided by the difference in time. And this is easy, and we could do this in any grade from 9th grade and on. We could have done that. But if I want to find the current exactly at one particular point in time, let's say that at 5 seconds I want to know what the current is, then I just take the derivative. Take the derivative of that function, f prime, and I find it at 5. So that's the application for derivatives of functions. You can apply it to anything. Let's apply it here to reactions. Mr. Wick will love this part. So the concentration of whatever product you're making a product out of two things. I don't know the technical names, but you can imagine what those things are. I can't. So you have two ingredients, and they react and they produce a product. So over time, there is more product that appears, right, as those molecules are combining and motion and whatever it is that molecules do. If I want to know the average rate of reaction, then I'm going to need 2 periods of time. I don't know. I want to know what happened between the first and the second second. So again, is the difference of the concentration divided by the difference of time, and that will be the average rate of reaction. But I may be more interested in the instantaneous rate of the reaction, because apparently these things happen very fast. So I want to know what happened at the 0.5 second, or I want to know what happened at the first second, or at 1.5 second. So rather than doing the difference of the y's over the difference of the x's, I can just take the derivative of this beautiful function that they will give me the equation for, and take the derivative and evaluate it at any value that I can. So I can find the instantaneous rate of reaction for that as well. It also works with volume and pressure. Now, the idea here is that we may have, I don't know, something, a gas or a liquid, and at the same temperature, if I apply more pressure to something, it's going to squish, right? So it takes less space, 3D, when I'm squishing, when I'm squeezing something. Okay, so the more pressure you have, the less volume you have. So I don't know, this equation may be exponential decay, I don't know, e to the negative x or something like that, whatever the function that is. If I want to find the isothermal compressibility, don't make me say that again, by formula is -1 divided by the volume times whatever the change in volume respect to pressure. So if I have an equation that relates V and P, I don't know, e to the negative P or something like that, I can take the derivative of this and find out what is that. Isn't it amazing? And also, it works for a population. Look at that. Population usually grows exponentially. Especially if you're talking about bacteria, that stuff really grows. So at different periods of time, you can have some kind of average growth. Their population is 10 million, and before it was only 5 million. So change in population divided by change in time, that would be the average growth. But you can also measure the growth at one instant, like after 5 seconds or after 6 seconds. I want to know what's the growth rate there. Then if you know what f is, again, the instantaneous f prime of t for whatever t you want. This average is only the change in f over the change in time. But here, derivative, instantaneous, always derivative. It works for velocity, average rate of change in velocity. I want to know how much the velocity change, but the velocity gradient, instantaneous rate of change of velocity, again, this is derivative. This is y1 minus y2 over x1 minus x2, like the other averages, but for instantaneous, you have f prime, also called gradient. For cost, if you happen to have your own company and you are making something, you may have a function that relates the number of units that you produce and the cost of making them. So you can have an average rate of cost, let's say, I don't know, for the 30th product and the 50th product. So I know that in average it costs whatever, change in cost divided by change in units. But the instantaneous is called marginal cost. And the marginal cost is nothing but the derivative of the cost function at that particular point. So for example, let me give you an example with numbers, because I know that you love numbers just as much as I do. I have a cost function, and it's a quadratic, and marginal cost will be the derivative. So let's just take the derivative very quickly. So 10,000 is 0, 5x is 5, plus double of 0.01, which will be 2x. So after producing 500 items, what would this mean? So C prime of 500 will be 5 plus 0.02 times 500, and that will be 15. Now, remember what the units were. I'm not finding C of 500. C of 500 will be the cost, the total cost of making 500 items. But that's not what this is. This 15 is not the cost of producing 500. This is $15 per item What this 15 means for 500 is that to produce one more, meaning to produce the 500 first item, okay, one more after the 500, it will cost $15 more. And it may be the same for other number of items, but if I were to do this for 1,000 items, this marginal cost may be less. It may cost less to make a unit after you make 1,000 compared to making an extra unit after you make only 500. So the applications are many. If I have an equation for demand and I take the derivative, I have marginal demand. If I have an equation for revenue and I take the derivative, I'm talking about marginal revenue. And if I have an equation for profit and I take the derivative of that, that will be called marginal profit. So in the examples that you do on the book, you're gonna see the power of the derivatives.